Well, good afternoon, everybody. It's 1:15 on Thursday, which means this is our Institute of Refrigeration Ireland summer webinar. So you're all very welcome. We have close to 40 people registered, which is fantastic. And this is one in the series of webinars we'll be running over June, July and August, and possibly into September. As always, thank you to our members and our corporate partners who keep the institute going and allow us to do what we do. So you might index the slides there, please, Seamus. Yeah.
Yes, of course.
Just the next one and the next one. Sorry, the previous, yeah, that one. So the draft inquiry, the draft revision, which is for the inquiry stage, has now been published. It's available on the NSAI website and is available on most, if not all, of the national standards associations across Europe or across the CEN area. It's available for free. You just have to register and you can download a copy. We'll be putting a copy of the standards on the resource on the Institute of Refrigeration IRI website probably tomorrow. So they'll be freely available to read. But if you do register, you can participate in the inquiry process and you can comment back through the NSAI or through the Institute of Refrigeration. So we'd very much like to see plenty of comments coming in. And the next slide then, Seamus. So last week we had a great presentation by Sazier Dixon from Frigobon on the use of A2L refrigerants and calculating the maximum charge and charge limits and so on. So that was really good. And the presentation is now on our website. And this week we have Seamus Kerr of RSL, who will be making a presentation on ammonia. So I think Seamus has about 5% ammonia in his blood because he's one of its biggest fans and quite right too. It's a fantastic refrigerant, but not without its hazards, which need to be dealt with. So Seamus is going to address some of these in the presentation this afternoon. So thank you, Seamus, and over to you.
Thank you very much, Declan. Yeah, so I'm Seamus Kerr. I've been working in the industry for nearly 30 years and probably cut my teeth on ammonia design back in the day. Just to talk a little, what I'll be talking about today is a little introduction to ammonia. EN378 is about a lot of things, including ammonia. I'll be looking at just some of the design recommendations, some of the changes in the new proposed standard. And then I'll spend most of my time just doing an example of how to calculate the working pressure of systems, and that working pressure calculation will determine the size, pressure setting of relief valves and your pressure test, tightness test, and strength test. Yeah, so I've put in ammonia as old as the hills. So actually, it was the 1875. It was Lindy, the famous Lindy, actually introduced an ammonia compressor. And it's as a successful refrigerant. People always think that ammonia is for very large systems, but actually, if you can see here on my screen, I've taken a little kind of commercial open compressor. It's running on ammonia. It's evaporated at -10, and its capacity is 7.3 kilowatts. So it just shows you that actually ammonia can be used on small systems. Ammonia wasn't popular in direct expansion applications, possibly due to the fact that it was difficult to clean the system. Expansion valves used to get stuck. Expansion valves weren't really available. But now actually we have electronic expansion valves with much cleaner systems. We have air-cooled ammonia condensers on stainless steel. And it's actually, I think we will see small ammonia systems in the future. And the old camping fridge that was in your caravan actually had ammonia in it also as an absorption system. Just to talk again a little bit about ammonia, some differences. So ammonia is corrosive to copper. So it's often used with the motors are often outside the system, or sometimes you can use a canned motor. And I see at the last year's Chillventa, some of the big chiller manufacturers, big screw compressor manufacturers do have semi-hermetic ammonia screw compressors. So there's a great future there. ammonia, I suppose, put it in simple terms, you need, for a refrigeration system, you need a lot less ammonia than you would, for example, 448. So we have a kilograms per kilojoule figure. You know, you have that's actually should be kilojoules per kilogram. Ammonia is about 10 times more, won't say efficient, but more powerful than a standard HFC refrigerant. I've mentioned the system, so systems are much cleaner now. Ammonia is a natural refrigerant. It's actually, pigs can make it sometimes anyway, so it's a byproduct of some chemical manufacturing processes. It's cheaper than your refrigerant and at a stable price. It is flammable, but it's actually, you'll see on the next slide, I'll talk about toxicity and flammability. So this is from EN378. This normally, these details normally appear in the first part of EN378, so part 1. But now there's a new, so in the 2000 and hopefully 26 version of EN378, there is going to be a part 5, and in that part 5 you'll find the details and the toxicities and various properties of refrigerants listed. So you see here that ammonia is a B2L, so it's higher toxicity, lower flammability. I'm going to just talk about calculating the refrigeration charge, but I'm not going to give any examples. I'm just going to show you, just highlight the fact that it's in EN378. So there's in Annex C of the 2016 EN378, you do have the charge limits. And this again is based on tables. So you're looking at two things as before. You're looking at the type of space that you're putting your refrigeration system into, and then you're looking at the flammability and the toxicity of any refrigerant. So there's the old 2016 table. So there's the two things you have to consider. And this is the same with the A2Ls. It's the same with any refrigerant. You're looking at, okay, who can be in the space? What's the kind of the hazard here? What's the risk? And then you look at then flammability of a refrigerant, toxicity of a refrigerant. So there was the two tables from 2016. So both your toxicity charge limit and your flammability charge limit. There is a change in the 2005 proposed. Excuse me, the one phone I didn't turn off. So there is a change in the 2025 EN378. So they're talking about the intrinsic design method, where you're looking at, you've mitigated for all the toxicity measures. So that's one way of calculating your charge limit. And then you're looking at the extrinsic design method, where you're looking at where you have additional toxicity mitigation measures. And that's all. So again, I'm only highlighting these. I haven't gone into all the details. And that's, again, both for toxicity and flammability. You're using the intrinsic and extrinsic design methods. Then to the fun part, the determination of the minimum value of system maximum allowable pressure. So from the 2016. So really what we're trying to do is to get a figure for, like, what is the maximum allowable pressure for this system. And EN378 often talks about a minimum value for that. So how do we calculate the minimum value? And when we're calculating that, so we should be thinking about the ambient temperature. So a refrigeration system in Saudi Arabia compared to a refrigeration system in Dublin should have a different relief calculation, should have different relief valves, because the outside temperature obviously can be much higher. Yeah, we also have to consider the accumulation of non-condensable gases. It affects the setting of the pressure relief device. We have to consider the method of defrosting. Is it electric? Is it hot gas? And then we have to think about the application. Is it cooling or heating? And of course, heat pumps then come into this, having both cooling and heating capability. Have to think about solar radiation, fouling, and then transport conditions. In the 2016 EN378, there was two methods. There was one where you could do all sorts of calculations and just show this is, so you'll be looking at the refrigerant, you'd be looking at the properties of the refrigerant and allowing for ambient temperature, solar, defrost type. And as a designer, you do the calculations and say this is the most this system will ever get to, and therefore I declare the working pressure maximum to be A, B, C. There's another method, method 2, which is pretty much everybody uses, is where we're using a table. And that table was in EN378. It's the same table in both the 2016 version and in the 2025 to come. So this is in part 2 of EN378, and it's in section 6, I think. Don't hold me to that. Pretty early on in the section anyway. So what we have here is we have a table that shows the various ambient conditions. And for those various ambient conditions, EN378 then guides you to pick a temperature to design your system at. So it basically says if you're in an area of Europe or the world that's the ambient temperature is less than 32 degrees, then and you have an air-cooled condenser, then you use the temperature of 55 degrees C to calculate the minimum value of your maximum working pressure for the system. And then they also suggest them for warmer parts of the planet. So if it's less than 38 degrees C ambient, there you use 59 degrees C as your design temperature, and again right up to 67 degrees C. So if you're somewhere in the world where it's you could have an ambient that could go above 43 degrees C and below 55, then you use 67 degrees C. So what does that 67 degrees C mean, or the 55 that we see here? So basically what you do is you look at what is my system pressure if my condensing temperature is 55 degrees, then what is my system pressure? And that's the minimum value. So that's stated. So you can't design a system with a pressure lower than that for any particular refrigerant. Of course, it changes for all sorts of refrigerants. So I have some examples here now. So here's an example. I've just said R134A in Galway. So we've taken an example here in Ireland. So there's the table. So I'm going to assume that the ambient temperature is less than 32 degrees. So I was going to say as the designer, but I have to say now as the person, and I'll explain that later. So as the entity who is selecting maybe relief valves and is deciding on the pressure, I'm saying that yes, Galway less than 32 degrees centigrade, and so that gives me a target temperature of 55 degrees centigrade. So I take my 55 degrees centigrade and I take any selector from, so you can use your slide rule, you can use your ASHRAE tables, you can use your Danfoss online app or your phone app and plug in your 55 degrees C, and that gives you then a pressure of 14.92. So that basically says in a system with R134A and the condensing temperature is 55 degrees, then the pressure in that system on the high side will be 14.92. So EN378 says you may not have a pressure lower than that for this system. So you can't say that system is a maximum 12 bar. It has to be whatever figure you choose has to be above 14.92. Then it's interesting, I suppose the next thing that we look at is, okay, the minimum value of maximum working pressure is 14.92 bar. So then the designer under EN378 2016, the designer can then specify any pressure higher than that as the pressure for the system. So your clever designer would, he can put in 20 bar, he can put in 30 bar, as long as it's higher than the minimum value. But obviously a good selection would be 15 bar, because the pressure you choose then determines the pressure setting of your relief valve, the pressure level of your pressure test, your tightness test, your strength test. So I've chosen a 15 bar. Many designers for R134A would choose 16 bar here, possibly because it's a popular relief valve size and it's not so onerous to do your pressure test, etc. But if we were to sail close to the wind, we can say, yeah, we'll have a 15 bar pressure relief valve. That means then under EN378 2016, part section 6.2.6.2, the pressure relief valve setting has to be no greater than 15 bar. So that's the relief valves you'd have on the system. And then that the relief valve fully open has to have a pressure of 16.5 bar. You can find that in the guide. Then when you come to put your system together and do your pipe work, etc., the tightness test is then set at the designer's declared working pressure multiplied by 1.1. So that means if you're doing your tightness test on the system, the tightness test is done at 16.5 bar. Just an interesting thing I came across in the new 2025 EN378 is that you can use CO2 as the pressure test medium if you can reach the PS value using the gas. So that means you're allowed to actually use the CO2 that you're about to put in the system to test the tightness. That wouldn't be allowed with R448 or R134A. Then just to touch on the strength test. So the strength test is the designer's declared working pressure by 1.43. So when you're doing your strength test before commissioning, in this case it would be 21.45 bar. Another little interesting thing that I won't go into in any great details is actually there's a different system for doing strength test for heat pumps, for reversible heat pumps. And there's a new figure at the PHIS and the PLIS, which you can go and find in the EN378 for your bedtime reading. I've taken another example of R448A. So if we go back to the table, see here, like 32 degrees ambient. Some people, and myself included, are seeing from a design point of view or an equipment selection point of view, 32 ambient. We're starting to see 32 ambients in Ireland. So if I was working in Spain, I would be using the 38 ambient always. But maybe we will start to see people using the 38 ambient here in Ireland. So for this example, I've decided, you know what, we're down in Wexford now. It's a lovely sunny day, and we're expecting warm weather for the next 10 years, next decade. So for the system, we've decided I'm going to use a 38 ambient. So now EN378 table 2 says that I should use a 59 degrees C. So I should look at what is my system, what's the pressure in my system at 59 degrees C. And so that's obviously different from the 55 degrees C figure. Also, just wanted to note at this point that 134A is a refrigerant with no glide. So it's a single component refrigerant. It doesn't have different refrigerants mixed together, so you don't have to think about dew point and bubble point. So just for your reference, I put that here. So when you take a refrigerant like 448A, 448A is made up of 4 components. It has some 1, 2, 3, 4 YF in it, and it has a glide, which means that the different parts of the system, different components are determining what the pressure is. So in an evaporator at 55 degrees C, which would be very unusual, the pressure would actually be 26.5 bar. But in the condenser, sorry, wrong way around, and this wasn't the place to confuse you. Sorry about that. So in the evaporator, you use the and I have to check this so I don't get it wrong. You use the dew point. So that's the first table here. So if you did have 55 degrees C and you're evaporating at that, your pressure in the evaporator would be 24.17 bar. But in the condenser, we look at the bubble point, and you can find these on your refrigerant sliders. So the bubble point gives, so at 55 degrees C from my Danfoss selector, I see that the pressure is 26.52 bar. At 59, so that's wrong. So I changed the slide, so it should be 59 degrees C there. I apologize for that. So I've put in the wrong, put in the comparison table instead. Okay, so taking that, so this is going to be higher, so we can X this out. But again, we take the same thing. We've got a minimum value of maximum working pressure, and then the designer under 2016 EN378, he can decide what am I going to say that the working pressure of this system is. Designer in this case would normally pick 27.5 bar. Again, it's a popular relief valve size. So that would be where you select his relief valves. And then for the tightness test, again, these figures are a little bit too low due to the wrong temperature. He'd be looking at a tightness test of 30 point something bar and a strength test of nearly 40 bar. The next one hopefully will be correct. So to look at ammonia in Dublin. So again, it's the same approach, table 2 in EN378. And this time, most ammonia systems are working on an evaporative condenser. So table 2 then has a part that says, okay, if it's an evaporative condenser, then you don't look at the 55 degrees C temperature. You can actually use 43 degrees centigrade. So when we take our 43 degrees centigrade, we pop it into our refrigeration slide rule, and that gives us a pressure of 16.88 bar. And again, I haven't done the whole calculation for this one. So again, you would base your relief valves on at least 17 bar. Your pressure test would be at 1.1 times that for your tightness test, and your strength test at 1.43. Again, I suppose in support of ammonia, nice manageable pressures. One of the great advantages of ammonia is that it's actually the pressures are quite low, so in that case quite safe in terms of any kind of ruptures of the system, unlike, for example, CO2, where we're dealing with pressures up over 100 bar. And talk a little bit about ambient temperatures. So I mentioned Galway and Wexford and Dublin. So in talk about some of the extreme temperatures that we had in Ireland. So in the 19th century, it's actually the highest temperature recorded in Ireland so far has been in 1887. So we haven't actually gone past that. I think it's a little bit, Declan might argue with me here. Let me have a look here, 33.C. So it is marked as the highest at the moment. So yeah, because I think the top temperature here was 33.0 in Phoenix Park 2 years ago. So we do have times in history where the temperatures can be quite extreme. But you see that we're up over this 32 ambient on a few occasions. So, and then just to look at the overall temperatures here, I'll give you a second to look at that while I put in my power, because if I run out of power, it will not be good. And I have it. So yeah, these are some of the, so see in our summer temperatures, okay, this was 1997, we had 28 degrees in May. In June, in 1887, we had 33 degrees, and then as young ago, we had in 2022 we had 33 degrees. So we probably, as we see, the general trend is for temperatures to rise, and obviously we'll be probably moving to the higher figure in the EN378. One point that I mentioned, I kept talking about the designer. One change in the 2025 proposed EN378 is that they're removing the mention of designer from the calculation of the working pressure of systems. And they're saying that instead of saying the designer shall, they're saying at the maximum allowable pressure shall be documented, the maximum allowable pressure shall be determined. So that's an interesting change. And then obviously it begs the question, well then who is this? Who shall determine the maximum allowable pressure? And so it leaves a bit of a grey area, and maybe Declan will make a comment on that when I hand over to him in a few moments. At this stage, I'd say thank you for your attention. Hopefully I've stayed well within the time. And then I'm going to hand over to Declan just to talk about our seminars coming up.
Thank you, Seamus. Yeah, thank you very much. Yeah, very interesting presentation. Yeah, there are a few changes. All right, the reference to designer and other duty holders, if you like, in the standard, they're by and large being removed across the standard, which is consistent with the general approach of standardization in Europe. So they're just being careful of saying of assigning responsibility to a particular person for the reasons of competition. They don't want to have anything in the standard that, for example, will make something fall in the responsibility of, say, a manufacturer, maybe at the expense of an installer. So it's not to say that the design doesn't have to be done or that there isn't a designer, but it's not ascribing particular duties within the standard. It still has to be done, but it doesn't make the standard easier to read. And I'm not sure it's an improvement myself. But that's the approach of SEN at the moment. So there'll be more about that later as we get our heads around it. So thank you, Seamus. Yeah, so there's a lot to take in there on the pressures. So we'll make sure that whatever Seamus mentioned there about the dew and bubble point is corrected for the
Yes.
when we save the version. Also, Seamus did the pressure. Some of the pressures he used were absolute, which is fine. You can use absolute or gauge. You just need to keep track of it. So that's where we are on ammonia. There's a lot more on ammonia in the standard, but of course the standard is much wider than that, and we should get probably a broader view across the board in terms of refrigerants at the webinar next week. So we're very, very pleased and honoured to have Dave Paget. David's extremely experienced in the industry. He's currently the chair of the technical committee in the IRI UK, and he's chair of the Mirror Committee for British Standards for EN378. Has won lots of awards, and he works in compliance at the moment, in-service inspection, and so we'll be delighted to have him next week. So he's representing the Institute of Refrigeration, our good friends, and they have several very useful papers on EN378 2016, and they're just about to run some of their own programs, webinars and meetings on the proposed revision. So Dave will give us maybe a heads up on that next week. So it'll start at the same time, 1:15. And the week after that, we have a notified body. We have HPI who'll be talking about the role of EN378 as a harmonized standard to the Pressure Equipment Directive. So that's their role. They have to make sure that when they're involved as a notified body, that EN378, where it has been called in as a harmonized standard, that is in fact implemented on the site. And a few weeks after that, in August, we actually have Jonathan Quigley from NSAI who'll be doing a presentation on how to participate in the process. So there's still plenty more webinars to come. So it just remains for me then to thank Seamus for his presentation and Karen for organising it. Thank you all for attending. We'll close the webinar. It'll be saved onto the website, freely available, and we look forward to seeing you next week. So thank you very much.
Thank you, everyone. Bye-bye.
Thank you. Bye.